the course on mission design was cancelled. I don't think we were too happy about it. There will be another lecture, most likely, I think, in December, with what Christoph should have been teaching. I'll step anyway in with the CubeSat lab. We'll start a little earlier. It was supposed to be starting in the second semester. We'll start now. I hope it will be a course with some fun. That's you will have to tell me then later. It's supposed to be practical. You're supposed to apply what you learn in other courses to design a mission. So that's shortly summarized. The goal is project-based learning. So I'm not going to teach you much. You will have to apply, figure out how things are being used, and I want you to design a CubeSat mission. More details to come. Taken from the course, the objectives of the overall course of the ISM. These are the learning outcomes that you should expect to know, things that you should know, and in the end, scientific, translate the objectives into system requirements. It's very clear if you design a mission. Do certain kind of analysis. Evidently, you will need to apply some project management techniques that you hopefully will learn or are learning. And we will use a number of softwares to that end. May seem daunting here. We'll keep it according to the hours that are assigned to you. That is, we're going to get here for an hour every week, and I expect you to work at least 1 more hour in addition. And I'll give you also some assignment for the break until next semester, so you have a bridge that you continue to learn a bit. Then when we continue this brings me to the overall, the global timeline. We're now here. We'll have now, say, half a semester to start that design exercise. We'll continue then with a full credit point in the second semester. And in the third semester, we'll use a prototype that the university is procuring at the moment, a CubeSat prototype. And then I want you to, what you learned here, to apply with the hardware. So the university is putting actually quite a bit of money to have a very realistic CubeSat in the laboratory, so it will be ready then. As you know, it takes a bit of time to finish that laboratory. Anyway, you will be working with real satellite hardware, and what we ordered, in essence, could be launched. So it's quite a significant investment that the university does for you here. So that here we should have a good understanding of the mission. From a theoretical design perspective, here should have a good understanding of what it actually takes to put that mission together. By the way, so this is a laboratory. Interrupt me at any time if I'm going too fast, but also if I go too slow. If you say, look, Jan, you annoy us here. We have heard these things 3 times already. They'll just make me speed up. Yeah? The plan for this semester. We're here. We're looking to the objectives of that mission today. Can you read that somehow, or you have it on your screen? You have your presentation? It's slightly changed from what is on the Moodle today. Objective of mission, and we'll figure out how we work together. And I will give you some assignments also. There's a slide on that, so that you get going. And then there will be topics to address, and each time there will be a short presentation, 20 minutes. And in particular here, speed up the lecturer. It might be myself, or we have 2 guest lectures. If we tell you something that you have heard already, or slow us down. We can, for example, if you want to repeat a bit the Kepler elements, that was a topic discussed. If the other always went too fast over it, here's the opportunity to go once more over it, to discuss it in detail. Mission. We'll start with the mission engineering next week. What does it take? Requirements, objectives, how do we break it down? What are the constraints? How to take that into account? And we'll focus on the astrodynamics for low Earth orbit. So there's particular things in low Earth orbit that are important for practical purposes, but they are not necessarily taught if somebody teaches you the Kepler ellipses. Yeah? Then the other topics: payload, week by week, system engineering, power engineering, communication, satellite communication, 20 minutes. I want to teach you, or want to work with you and teach you what is really relevant if you do a CubeSat mission. Most likely what you learn in SATCOM lab, it's an overkill for CubeSats. Altitude control and command and data handling in the end, and we will end of December, where each of you will then give a presentation. But this is what, let's say, these are the topics of each week. So there will be a short presentation, but then you will work on designing the mission. This is what is in the group work. We'll start with some literature review. We have an easy beginning. We'll look into requirements, and then you have to do a system analysis. You have to work on your mission. And then there will be assignments. As I said today, I'll give you, there's a slide on it with some things to read. Those who have had a look into the Moodle saw it already. Should not be too much, but we'll need to get going somehow. Yeah, so whatever you have worked out here, I want you to present that in the end. It's an opportunity to give a presentation, to practice your presentation skills. I can tell you that when I was in my master's studies, I was a lousy presenter. Now I dare to say I'm not so bad. And the difference between the student, young children, the master student, and now is simply practicing. So I want you to give each of you a 10-minute presentation here. Who has difficulties to pass a message, come to me. We can make a rehearsal. Yeah. It is giving presentation. It's an extremely important part of professional work. And if you have been to a scientific conference, you will see, like the CubeSat symposium, for example, we see many people fail that actually. So when I come home from a scientific conference, the only people it's usually few people I remember presenting, and it's only those who were able to pass a message. So it's a valuable opportunity for you to give a presentation. Next semester will look similar, maybe some more specialized topics, and then there will be the final presentation of semester 2. That will be part of your examination.
So there's going to be a written exam?
Say it again?
So there's going to be a written exam? Or
no. I think will be also on the slide. Well, I'll come to it. The details about the examination in a minute. Yeah? So how do we do it? We'll divide you in 6 groups. I defined 6 disciplines, engineering disciplines. We'll group around this science here. They're a little low tech, but they will do the job. And then each of you will have to treat one aspect of mission design. System engineer, so it's taking care of the entire satellite. To some extent, also the ground segment, power engineering, communication, like the topics that you saw before in the table. I have a group of 2 persons. By the end of my presentation, we will do that assignment to the different groups, so you can already pick one. There will be 2 per each. Not everyone will get maybe the group that he or she wants the most. We'll define that at the end. Each of you will then work. And then each group will work independently. Within this very small group of 2 people, you should try to arrange yourself. Also, teamwork is an important part of professional work. Also, here many people fail. And yeah, I mentioned already there will be topical lectures as part of this CubeSat lab. Contacts, you should know where to reach me. Email address, it's written here anyway. My office is in that building, E building, 2nd floor, At the moment, I'm the only person on that floor, so you can't miss me. Yeah? At some point, there will be more people there. So there's also space. Just since today, the door is locked. So yesterday, you could have just walked into my office. Today, it's not possible. You need to call me, for example, on that number, or write me an email for so that I can let you in. Yeah? I reserved the time before that lecture. So on Thursdays from 1 to 3, I'll be in my office and I have time for you. That's reserved. Is there anything you didn't understand, perhaps with the homework, the assignments, or anything else, I will be there. At any other time, you can send me an email or come to my office, but sometimes I'm having meetings or I travel, so then the time is simply reserved for you. Yeah? Well, so, one more step. How do we work together? I mentioned already the groups. I want to have a very classical engineering approach with you, with small adaptations to it. Imagine we are a manufacturer of automatic teller machines, cash machines. We build this, and we have a customer who wants to buy one, say a bank. The customer is not only defining what the customer wants, because there's people who will use it. When you go to your cash machine, you use it, but you don't talk to the manufacturer of the machine. All right? Then you may be complaining to your bank saying the machine is not working, or the bank may do a survey. What does the user want? Anyway, we are building a space machine, say a machine. We have a customer, a bank, and the bank has users of it. Customers are the guys with the money that define requirements. No, so they define constraints, while the user defines requirements. For example, the user may say, I live in Luxembourg, I want that the machine works in German, French, Luxembourgish, and English. May not say that so explicitly, but the customer may know that, defines this as a requirement. The customer puts that forward, these requirements, to us now, together with some constraints. For example, the bank may say, yeah, okay, I want to have a high fidelity ATM, but it shall not cost more than 10,000 euros, budgetary constraint. Or it needs to be ready in 2 months. It shall have my branding, International Luxembourg. So there's a difference. There's important things to learn here. Requirements. The customer receives the requirements, transfers them together with certain constraints to us, to the design team. And the design team breaks it down into steps. The dispenser kind of boxes. A bank card reader, some kind of computer. There are certain subsystems. And that will be you, so your groups, for which will be defined subsystem requirements. And certain things will not be done by design team, that will be outsourced. It could, for example, be that the contractor does not do the installation of the ATM, but it sources this complete out, this part. Or part of the subsystem is not within the competences of the contractor, of the manufacturer. It's outsourced, so they are subcontractors. In our case, the design team will design a CubeSat mission. You, actually, I will be the customer, so I will define constraints, and then there will be a user. And in space missions, that's usually the scientists, most of the times. Yeah? So they say we want to observe the sun, we want to observe the Earth, exoplanets. Scientists say usually what they want, requirements. Usually space agency is the customer. They have the money. They define these constraints that I mentioned. very fine what all the scientists want, but this is the budget we have. Either you do it with that budget, or we have no. You will be design team, and you will not do everything. You will outsource certain things. You will possibly buy certain things.
This is mainly accounting for manufacturer who are making custom-made product, I would say.
Yeah.
If I just want to buy a printer, I will not tell the manufacturer I want a printer of this price.
So,
Yes.
So, and how far would this be differently?
so if you're talking, there's one thing is consumer products which are ready for a specific purpose. Most of the time, space missions are not there that you can just buy for a specific mission. So that is, let's say, a main difference, that space missions are usually not, the entire mission is not off the shelf, or the satellite is not off the shelf. If you have a need for a mission that is very similar to another one, for example, most likely you can buy a satellite. Most likely, if you go to a main CubeSat manufacturer and say you would like to have a satellite that can take an image in the visible with a resolution of 10 meters, then most likely a CubeSat manufacturer could see which other customers he or she has served already with that very common objective and then take it. Most likely would still be adapted, because this technology evolves quickly over the years. These projects take years. So there's a specific, say, aspect of our carriers in space is that projects take many years, in contrast to other professions where projects takes months, weeks. Ours always take years. So technology develops. So even if they had a customer with that particular technology, it might be outdated. Obsolescence could be something. So you cannot say, maybe not repair it or not refurbish. So what you're talking about is about a product that is for which many varieties exist, and most you can find it serving your purpose. That's usually not the case for these space missions. Yeah. By the way, since we do research and science here, it would not be, we would fail here if we were to do something that has been done before. So while I present you the requirements and the constraints, they will be challenging, and so you achieve that, which I don't know by now. Yeah, if that's actually achievable, then it will give added value to what exists. Otherwise, so I would fail here in a university if I would not give you a challenge that is not really new.
So we could say that the workflow for consumer projects is out of the scope for this class.
Yes. Well, if you find, I'm giving you then, so I looked into the science and say also a little bit in technical feasibility. And I think that I will present you requirements on the next slides that cannot be accomplished with an existing mission. That's what I believe. Now, if you find that, then I failed in setting up a novel objective. So I'm quite confident.
I would say that even consumer products have innovative components and are new all the time. Like the newest Dyson Hoover will be new again, and will be developed.
Okay.
But still, it's different to this kind of.
Okay. First of all, about Dyson would be quite cynical, but so yes. When there's a new generation of cars, they are, of course, new. They are not specifically designed for a particular request of a customer. They kind of estimate what the customer wants. By the way, in this setup, customer and users are the same. If you buy a car, they push that forward. They assume that and see if it sells. In our case, it's different. It's more specific. As you said in the beginning, we want something that is very specific to our purpose. basically almost on its face. First of all, there's no consumer products there, and then the customer and users have very specific needs because they're usually very often scientists. Even if you have business ideas, it's usually new because also business idea needs to be new. You don't have to repeat what others were doing. Yeah. Okay. So the scientist. Who's the scientist here? It's Tony. We picked a topic that she knows is her specialty. So you have to satisfy her requirements. I'm the customer. I'm giving you some constraints on the next slides. You should have a boss in your contractor who defines from the system requirements and constraints subsystem requirements. And here we deviate a bit. We have no boss here who will distribute that work. So from these system requirements that you will receive and constraints, you will define yourself requirements for the different. To give an example, your measurement method needs maybe 100 watt. Means from the system you need to define the power system needs to produce 100 watt. This you need to do yourself, and then you can further elaborate on the further subsystem requirements. And you may look into, and it will be part of KIPSATs, you may look what is commercially available. While the mission is not available commercially, many of the subsystems actually are. So, these are the scientific requirements. I want you to a measure of the soil moisture of the world's land mass, so, which is only like 30% of the entire Earth. How much water is there? Ice, snow, or just liquid rain? I want that the entire Earth is covered once per week with a resolution of 400 square kilometers. So for each point on land, with say, or with a square of 20 times 20 kilometers, I want each week one measure how much water there is. I want that information not later than a week. Either you downlink from your satellite the data very regularly, but latest a week after the measurement, it needs to be available to me, actually to the user. Should be more specific. And the mission shall take a year.
So is this the assignment?
That is the mission that I want to design until the end of the second semester. It's by the end of the first semester, and so in December, I want you to already have a good idea of how that mission shall look like. It's a topic of research, people do that already, will become a little more clear quite quickly. Very typical user requirements. Tell me?
What does mission duration mean in this context? Does that include the planning, or you will collect like a hypothetical?
Say it again?
What does mission duration mean in this context?
So I want for 365 days that piece of information. So what are the implications in that? Your satellite or your entire system needs to have a certain reliability. It shall not break within 2 weeks. It may mean that your satellite has to have a certain altitude. If you launch your satellite into an altitude of say 300 kilometers, it will experience a lot of drag and will slow down after 2 months. No, it will burn actually after 2 months. So then you would be violating that requirement. Any methods that you